Okay, so we're going to look at the relationship between the potential difference across a resistor and the current flowing through it. Now, really important to note that voltage and potential difference are the same thing. So if you ever get asked about potential difference in an exam, it means the same thing as voltage. So potential difference and voltage are measured in volts using an instrument called a voltmeter, and current is measured in amps using your ammeter. So the first part asks us to draw a graph of voltage against current for these results. So it's very similar to coordinate geometry in maths, where you've got an x and a y axis. You can see here that current is on the x axis and voltage is on the y axis. And we'll just write the same thing up here in our table. So current is on the x and voltage up here is on the y. So like in maths, we look at the x-axis first before we look at the y. So we'll go to current first, 3.6, and then we're going up to 2 for the voltage. So 3.6 up to 2 is roughly around here. Okay, we then go to 7.2 for current, and we're going up to 4 for voltage. So 7.2 up to 4 will be about here. Then we go to 10.8, so 10.8 and 6 on the voltage, which is here. 14.4 up to 8, and 18 up to 10 volts, which is there. So we then get a ruler and join all the points together. The line should be going through all of the points. Now the first one is a little bit off. That's just because of the pen that I'm using on the iPad. But that line should go through all those points, which leads us on to the next question, which is asking us, what is the relationship between voltage and current shown by your graph? So because it is a straight line, we say that voltage and current are proportional. So that's the answer for the first question. So the next question is calculate the resistance of the resistor. And when we're calculating resistance or voltage or current, we have to use our formula. So the formula is voltage divided by current, which is represented by the symbol I, multiplied by resistance. So it's in a triangle like that. So if we're looking to calculate the resistance, we block out what we are looking for and we look at what we have. So to get resistance, it's voltage divided by current. So we go to any point on the graph, or you could use your table, of course, as well. So if we look even at the table, we can say that when the voltage is 8, the current is 14.4. So 8 divided by 14.4 is going to equal 0.55. So we'll round it up to 0.6. And the symbol for resistance is measured in ohms. So the answer is 0.6 ohms. And that will be the symbol for ohms. The last question then says, what happens to the resistor when current flows through it? So when current is flowing through the resistor, the current is going to decrease. That's one thing that might happen. Another thing might happen is it will get hot. Okay, so the resistor will start to get hot when current flows through it. Okay, so moving on to the next question. The diagram shows a circuit containing a light-dependent resistor attached across an ohm meter. Light from a lamp shines directly on the LDR. So the first question is, how could the intensity of the light shining on the LDR be changed? So I think that is fairly straightforward. If you want to change the intensity of light, you could move the lamp towards the LDR or away from the LDR. You could change the bulb. That could be another way that you want to change the intensity of the light. Okay, so the next part says, using the axis on the right, sketch a graph to show how the resistance of the LDR is affected by light intensity. So an LDR is a light dependent resistor. So it needs light in order to have resistance. So towards kind of the origin of the graph here, that's where there's no light and no resistance. So if there is no light coming towards the light dependent resistor, the resistance is going to be really high. So you can see here that there's not much light intensity here, which means we have a high resistance. But as the light intensity increases, the resistance starts to drop and gets lower and lower and lower. So the more light an LDR gets, the lower the resistance. Okay, and the next part of the question then says, state one use of an LDR. So what we talked about in class with LDRs were for street lighting, okay? So all you need to say there is street lighting. Okay, and part C here, a student set up the circuits shown to investigate how current flows through a light emitting diode. So that's our LED. Now we know that in our LED, the current will only flow when the LED is forward biased, which means the positive part of the terminal is coming into the positive part of the LED. Now, in our cells, okay, which are here and here, you can see that there is a longer side on the right compared to the shorter side on the left. This longer side here indicates the positive terminal, and the shorter side here indicates the negative terminal. So the best thing to do here is we'll just write it in. So here we've got the positive side and here is the negative, and we'll do the same on the other circuit. So we've got our positive up here and our negative here. Okay, so we know that the diode allows current to flow if the P terminal is connected to the positive of the battery and the N terminal is connected to the negative of the battery. So let's look at circuit diagram A. We can see that this part of the LED is the positive part and the other side is the negative. So if you see the black line attached in the circuit, in the symbol for the LED, this indicates the negative side of the LED, whereas the triangle indicates the positive side. So in circuit A, you can see this is the positive of the battery, and if we go in a straight line around the circuit diagram, we're hitting the positive, the P terminal of the LED. Let's go to the negative line and we continue from the negative line around the circuit diagram, past the resistor, and we're hitting the N terminal. Okay, so the N terminal of the LED is hitting the negative of the battery. We go over to the other side in circuit diagram B, positive of the battery. If the switch was closed, we go around the circuit diagram and we notice that we're hitting the N terminal, okay? And then we look at the positive terminal, follow the diagram around, and we're hitting the negative. So we should be able to see straight away there that this is not going to work, okay? We can't have the positive part of the battery going to the negative terminal of the LED. Positive has to go to positive. Negative has to go to negative. So the first question asks us, in which circuit A or B would the LED light up when the switch is closed? So it will light up in circuit A. Okay, so then we're asked to explain our answer. So we can just go back over what I said there. So for current to flow, the LED has to be forward biased. So the positive part of the battery has to be connected to the P terminal of the LED. Okay, so it's forward, has to be forward biased. And the last part then, it says state an advantage of using an LED instead of a filament bulb. So LEDs use less current, they're cheaper and they're more efficient. So any one of those three will give you your 3 marks.